Welcome to the joint seminar at TILOS and HCSI. So today we're thrilled to have Professor Jason Lee visiting us and giving us the talk. He has loads of awards, and he's an associate professor from the electronic engineering and computer science at Princeton University. But without further ado, let's take it from here.
Hi. Yeah, sorry for the delay. Luckily, this talk is really 40 minutes at most, so we're perfectly on time. It's joint work with two of my students, Ishan Muchani and Alex Damon. Alex is applying for jobs this year. So yeah, he's an excellent theorist, empiricist, extremely rigorous in the science of deep learning. Oh, sorry, wrong device. So today my goal is to talk about how transformers can learn causal structure. An important example of this is motivated by Anthropic's blog post from about 2 or 3 years ago about induction heads. So I'm going to start over there. So let me talk about this Anthropic blog post. They had a series of 2 blog posts, one of them called ICL and induction heads, and another one called Mathematical Circuit Perspective on Transformers. Extremely long. I think combined they're easily over 200 pages in which print. It's very long. So this was their first attempt essentially at mechanistic interpretability. Do I need to stand here for people for this to hear? Okay, so basically what they found is that if you train a one layer attention only transformer, the loss will never go down if you measure the in-context learning ability. But as soon as you use 2 layers, 3 layers, 6 layers, for this small experiment, they did attention-only transformers. I'll show you later with like GPT style, like decoder transformers with MLPs. Basically, what they observed is that the in-context learning ability, it really requires at least 2 layers. And also that it Hello.
Oh, yeah, okay.
Okay. There's another prominent example of in-context learning that's quite simple. This is from a paper from Greg Valley and Percy's group. Basically, the idea is you're doing supervised learning, but I don't let you, and then I just feed all the training data as a long sequence. I don't let you do gradient updates or training. It only goes through the forward pass of the transformer. So basically, you can frame the, of course, supervised learning as an X token is you just in what comes after X test is you want to put like the conditional expectation of Y given X for regression, for example. So this is also another type of in-context learning. So kind of the two examples I have in mind, the simplest ones are this one and the Markov chain. And notice these are both in-context learning, but they have different dependent structure, right? Here, the Y's parent is the corresponding X, but the X's have no parents. So this graph is like, it's just a bunch of disconnected components. So that's the causal structure. Okay, so how would an induction head approach this is basically now you look for who's your parent. Every Y's parent is an X, and those are copied down, and nothing happens for the roots. X's are roots because they have no parents. So the DAG looks like this. Okay, so those are the two examples I went over. Markov chains. This is essentially what Anthropic did, how they meet their data. And the second one is this supervised learning, but you don't let yourself train. You can think of it as meta learning if you like. And you can be more complex, right? There's many possible causal structures. So what kind of the motivating question for me is to look at when you pre-train transformers, how does this particular architecture solve this problem of learning the causal structure and then using it to help predict the next token? So we'll sort of follow what's common in the paper by the Stanford group and Anthropic is they both essentially use a meta learning setting. Is you construct a family of in-context learning tests, sort of like meta learning, that require learning the causal structure. So between sequences, what's shared is the causal structure. And then I'll analyze the dynamics of gradient descent. Okay, so let's see how to set up the ICL family for Markov chains. I'm going to just draw a transition from this prior distribution. It's not very important. I'll just say Dirichlet for simplicity, each row. Then I sample the first one from the stationary measure. And then after that, I sample conditional on its parent. So just drawing data in this way, it will always satisfy the Markov chain DAG, the independencies in that DAG. And again, sort of the most natural estimator is to compute the empirical counts in context. I take my sequence, I look how many times S goes to S prime, and divide by the number S in a sequence. And this is why length helps. If your sequence is too short, you just have incredibly bad estimates. For more complex causal structures, we'll do something similar. It's just a way to generate data, sequential data that always respects the DAG. For all of the dynamics part of my talk, I'm only going to talk about when you have a single parent, and I'll talk about at the end what happens in multiple parents. So when you have a single parent, again, you just draw a transition matrix. And now the only thing that changes is you condition on your parent instead of the one right before you, because the parent might be a lot before you. And again, you predict the last token. Okay, so the point here is this kind of way of generating tasks, the probability distribution in every sequence is different, but they factorize in the same way. They respect the DAG, but the actual transitions are always different. So there's no way you can, like if it was Markov chains, I could not use the transitions from the previous sequences to help me. They're just different. I mean, they share a little if they're from Dirichlet priors, but that's pretty negligible at the level I'm thinking of things. But what is shared is the graph, the DAG structure, the edge structure. So this problem is not so easy to kind of the eyeball. If I just gave you a bunch of sequences drawn from some DAG, it's not so easy to figure out. Like here, these are drawn from the same DAG. It's not so easy to guess what the underlying DAG is because the transitions are different. Like I can make them small and big and so forth. Okay, so a smart learner to implement the maximum likelihood kind of idea, what it would do is it first uses the information between different sequences, combining that to learn the graph. And then it just uses the test sequence to estimate the transitions. That's sort of what I guess sort of the most natural estimate. Okay, so once you know the parent structure, it's quite easy, right? You just count transitions. Yeah. Okay, so the more interesting part of this two-step algorithm is the first stage, is how they recover the graph given many different sequences. I'm going to go into a detour of how Anthropic thinks about transformers again. So in the same blog post, they spend a lot of time talking about these things called residual streams. More or less, residual streams are the analog of like memory. Like every time after a block of the transformer, be it attention or MLP, they think of it as being added back into the stream. And then the next operation reads the stream. It does its say MLP and then adds it back. Okay, so that's kind of what this picture is saying. Everyone's reading, doing its operation, and then adding it. So in their sort of a way of thinking, this is not math. This is just how they believe transformers do things. The residual stream is very big, and the transformer knows to read, like, for example, if I do a computation and then you did a computation, and then much later, I need to know that this came from 10 steps ago and this one came from 12 steps ago. And I need to be able to know, like, have a pointer to read them separately. So they're kind of thinking of these subspaces as very high dimensional, and you're writing on sort of near orthogonal subspaces. They can't be perfectly orthogonal, otherwise your embedding dimension would blow up. But so the way they write things is that, like, it's like we're reading from these like near orthogonal ones, so we can store almost exponential things in the embedding dimension. You can probably imagine that this gets quite messy. For the representation and approximation, it turns out not to be too bad. Is that we do know that if you write on nearly orthogonal subspaces, the potential interferences are controlled. But for dynamics, I don't think it's super tractable. So yeah.
Did they have density sampling? I feel like it would be pretty easy to just like do inner products and look at.
Yeah, they tested and they've gone. Yeah, they're sort of the one company that really does a lot of this interpretability. They've tested this residual stream hypothesis, and they've also have ways now to like disentangle them using autoencoders, where you try to like separate the streams. You can think of it, it's kind of like sparse coding, right? Like you have one thing plus a randomly rotated thing. How do you disentangle? And they started using like autoencoder type things. They have a bunch of stuff. Yeah, like trying to, and it's like roughly at the level of like things we can understand. It's one of the more solid things. Yeah. Induction heads and residual streams are kind of the most solid things I would say in mechanics. So instead we took an alternative, which is motivated by, it's very similar to this paper, also on mechanistic interpretability on grasp. Is sort of, you just don't want to think about this entanglement and every time figure out how to disentangle. So what we're going to do is very naive. We're going to, instead every time we're just going to concatenate. Okay, so in the residual stream view, you add, you multiply by like, say a random rotation and then you add. So then when you want to extract it, you do like the rotation transpose or something. We're going to do the simplest thing, which is just concatenate. This way you always know what positions it in, how to read it out. And now when you train a transformer, you know which block hopefully does what, right? In that sense. And we're also going to look at the case where there's no MLPs. So they show that both the MLP with and without induction heads are common. You definitely don't need MLPs for this task anyway. So we just remove the MLPs. Okay, so in terms of expressiveness, you don't lose anything. These things called disentangled transformers that people in MechInterp use, they have the same expressive power as regular transformers. But what is the cost? They're completely impractical in the sense that the embedding dimension is massive, right? Every time you, like say the embedding dimension was 100, now you 200. And then next time for each of those 200, each of the 2 blocks, you append 2 blocks. So now it's 4 blocks. Then it's 4 times 2, it's 8 and so forth.
The W.
Sorry?
So the W0.
Oh, it's the output embedding, output.
It's just the embedding.
It's just, it's giving the output. It's like the final linear head. Yeah, it's a final linear classifier. Yeah.
Can you say theory?
Yes, this is easier. Yes, yes. But this is just representation, expressivity. It's just saying I can, for every regular transformer, I can write down one of these. It might be good. And this is really easy, actually. Yeah.
But I guess in terms of training, usually when you train transformers, you train those sort of transformation matrices.
Yeah, yeah.
And here, when you train.
Here, it's the same thing. The weight, the attention has weights in it. And if there were MLP, the MLP would have. Yeah. It operates token-wise, so there's no way for the MLP to look at. Yeah. Attention is the only operation, can mix between.
So the attention layer, you're using the RAGU vision.
Softmax. Yeah, the structure. Softmax. Okay, yeah, so, but the advantages of it is why people have designed it, is you can interpret it. The original paper was, it was even trying to like take transformers and decompose. There's a language called RASP, which is like a way to like program transformers, roughly speaking. And they were taking these disentangled transformers and decompiling it into RASP. So like, it's nice in the sense that you have a better chance of reading off what it is. And we're using it basically because now we can track like every parameter we hope gradient descent with. Okay, so disentangled transformers is also easier to visualize what's happening. On the left is the adjacency matrix of the change graph. Then I plotted the first attention. I trained a disentangled transformer. And kind of the surprising thing, or not that surprising, but And this is what Anthropic basically already solved, is that this first attention, the position block of the first attention looks like it matches the adjacency matrix. And Anthropic didn't have this heat map, but they described the mechanism in which they think transformers solve the task, and that mechanism corresponds to this attention pattern. The second attention layer, notice it's huge now, it's a 4x4 blocks. This token one is identity. And I'll explain what that corresponds to in a minute. And this is just the readout, the WO. That one doesn't really do. You don't really need it for this task, basically. Okay, so yeah, first attention matrix is adjacency of the causal graph. We tried playing with some other causal graphs. So Anthropic only talked about Markov chain graphs. So we tried the same thing for other causal graphs. And we found that the first attention, the sparsity pattern matches the adjacency. And this was sort of our starting point, is that if it matches the adjacency, it very likely uses that estimator that figures out your parent structure and then does the counting. So that's what our goal would be to show. Okay, so let's describe now how, this is basically what Anthropic tells you, observed empirically, is you first figure out who's your parent. That's what the first attention tells you. So for this graph, it's just you point to one before you, and then it's copied into your residual stream. Normally it'd be added, but we're just doing copy. So that's why I shift everything downwards, but diagonally. So now in the residual stream of the last token, there's now B and then C and so forth. And then the second attention layer, that was one of these blocks. One block of it was an identity, is it compares the last token to the residual stream. And then it matches the ones that it attends to only the ones that match, that are a perfect correlation. And then I look, the ones that match, I go up one level, because that's the token that followed that one, right? It's like I shifted the sequence. If I go up, it's a token that follows you. Okay, and that gives me the answer, because there were two A's and they were followed by a B and a C. So the distribution is half B plus half C. And it does this in parallel, for all of them. But we're only predicting the last one. Okay. Oops, no, back. There's a lot of parameters here. What we were only able to analyze is training the two attentions. We're only going to train this. We're only going to consider training this block and that block, the two attention blocks. So this disentangled transformer had many blocks. It's like 4 times 4 plus 2 plus, it's like 20 blocks or something. Okay, we're only going to look at training 2 blocks. But the two, because I mean, the motivation was the other blocks were really 0, but it's not so easy to prove that they're 0, they go to 0 and don't affect everything. And we're just going to just ignore them and fix them at what's 0. Okay, the loss is cross entropy for predicting the last token. The theorem is that remember I have these transitions for the family of tasks. They need to mix. So I'm just going to assume a very strong assumption on mixing is they're just bounded below by a gamma over S. S is number of states. The first part of the theorem, it just says that the loss goes to 0 as sequence length goes to infinity. So it's like 1 over T to the gamma. And the more interesting result is the second part, which says that the attention matrix, its sparsity pattern, it matches the adjacency of the graph at 1/t. So the first attention is truly learning the DAG structure. And there's also one for the second attention, but it's not interesting. Second attention is just doing a hard max because it's trying to match the last token to all the other ones. So it's just a hard mixing. So you just take something like a identity in the right position and send it off to infinity. The more interesting one's the first one. Okay, so as a corollary, if your sequences all come from chain graphs, you do learn what anthropic described. There's also an OOD result is you don't need, in a future sequence, you don't need to have seen the transitions before. They can be out, they can be not in the prior. Let's say the prior was uniform on like a narrow interval. Now I can use transitions outside of that in their work. They still need the lower bound for the mixing, otherwise the in-context estimator is crappy. But as long as you have the mixing, it still works, regardless of if it was in the prior or not in the prior.
So the previous result for is for any tag or a single parent?
Single parent. Yeah. Whenever I talk about representation, it's for anything. And then whenever it's dynamics, it's single parent. Yeah.
Optimizing the two blocks, you're optimizing just the blocks corresponding to the position embedding first, and after that is fixed, you learn the second, or are you optimizing jointly?
Let's see. You need to train the first attention first, and then the second one. But in reality, I think what happens is a little bit like three phases. I think the true dynamics are the second one becomes like 0.01 identity, something tiny, but in the right direction. Then the first one learns roughly the adjacency. Then the second one starts shooting to infinity, and the first one almost doesn't move. But what we can prove is training the first one and then just the second or both together. The first one, yeah.
That result because it's infinite.
No, it's this T.
Yeah, so number 2 over here. So T is actually the
T. S is just number of states. Oh, all numerators, all ES for sure. Yeah.
Sorry, I was thinking that T is a number of iterations.
Oh, no.
So yeah,
Number of iterations with infinity.
Yeah, I forget. The number of iterations is polynomial. Like, the number of iterations is poly and T and C. Yeah. But this is population. Yeah. I don't know if the how hard it would be to do like stochastic. Yeah. Okay. Let me I have 10 minutes. Let me talk about kind of what I think is the main lemma. And so kind of the main lemma is the gradient is almost equal to the mutual information between, so you take the gradient, the first attention, look at the ij, and it's very close to the chi-squared mutual information between I and j. That's the definition, the chi-squared mutual information. This is a happy coincidence because the position I will attend to J, a predecessor that maximizes the chi-square mutual information. Because the gradient is most negative in that direction, but most, whatever, you know, if you follow the negative gradient, that one grows fastest. And then we have data processing inequality. By data processing equality, the mutual information is maximized at your true parent, at your parent. So the gradient, think of it as a vector. I fix I, and then I look at it for all j less than I. The entry at which is biggest is the parent. That's what data processing tells you. And we just follow this gradient. I think it's combination of things, yes, but the softmax is important. Yeah. It's because like the loss is KL, but itself inside is a softmax. Yeah.
Because the tag is nicely ordered, right? Because otherwise it might.
Yeah, you only attend the ones before you.
Yeah.
Yeah. That's weird. Okay. So for example, in this Markov chain, it means that the one right before you, the position right before you is always the largest in the gradient. And then, so they all shoot to infinity, like maybe the information is 0.9 and then 0.8. They all shoot to infinity, but because it goes through softmax, only the largest. The ones that grow slower, they get squished by the softmax. Okay. So in general, you can only decrease this information by attending a non-parent, so it's maximized at the parent of y. And this is the sketch for y. If you ran gradient descent on just the first attention, you would learn the adjacency. It reminds me of Chow-Lu, kind of. If like Chow-Lu is like unknown ordering, but like let's say a even more basic form of Chow-Lu is I just tell you you can only attend the ones before you. Like probably what you would do is just compute the mutual information, choose the largest one. Yeah. Let me spend like 3 minutes on when you have general DAGs. General DAGs are interesting to me because they contain one very special case, n-grams. And n-gram is exactly like a 3 gram is a degree 2 one. You attend 1 before and then 2 before. And in general, you attend n-1 before. So if you can show you learn n-grams, at least transformers do as well as NLP around 2008, let's say, which is not bad. So we have constructions in the paper. I think there's 2 pretty simple constructions. I'm presenting the one here that uses multiple heads. Basically, for this causal graph of a 3 gram, the first head attends to one before. The second one attends to two before. And in general, you can always have this, like basically the degree of the graph is the number of heads you need. Degree -1 is the number of heads you need. Here are some other causal graph. You attend to 1 before and I/2 before. And one head handles one and the other one handles the other. The gradient descent dynamics is very challenging. There's also a depth construction. And we did some experiments to see, so like if you use a minimal structure that matches this construction, it will learn this. And same thing for the depth. If I make every layer only have one attention head and use the depth construction, you'll learn that. But then if you train a big one that contains both of these, it's just an uninterpretable mess. So I actually don't know which one is preferred, nor do I know how to train either of them. It's very challenging. It's essentially the same difficulty, or at least as hard as training a 2-layer neural net. You can just think about every head as a neuron. And then the issue is there's a symmetry when you initialize. Let's say you initialize a 0. You would like, then if at 0, every head would learn the same thing. But so at some point they learn the same thing and then they need to split and then learn different things. But there's like in neural nets, we know how to analyze this when they're like orthogonal. I have no idea what orthogonal means in our heads. I mean, we assume the data is Gaussian and then orthogonality is like the right notion of like decoupling the neurons. But here I have no idea. There's this excellent paper by Ben Edelman and some observing this sequential behavior that shows you first learn the best unigram approximation, then the best bigram, and then the best trigram. The data was generated by bigram. This is really nice. It shows this staircase sort of learning behavior. Unfortunately, we have some counterexamples that show like the best bigram is not a subset of your true parents. So like this would be really hard. Let's say you learn the best bigram, now you need to forget it to learn the right parents. Yeah. Anyway, so what I talked about today was some simple case where the chi-squared pops out, and then you can learn the adjacency matrix. As a corollary, you do learn the induction heads Anthropic described. There's some nice connection between like things like Chow-Lu greedy graphical model estimation and what gradients are doing. I like this disentangle transformer for almost all the things I work on now. With dynamics, at least, I kind of choose to use this. Otherwise, it just doesn't feel doable. Kind of this mechanism so far is very not general. It only looks at attentions on positions, right? Like sort of what I would really like is that like some sort of attention that looks at context and positions. Yeah, I don't really know how to, yeah. I'd be happy to hear any like simple models that have these properties. With some work we can analyze. Yeah, thank you.
It's a very interesting model to have the training data coming from say different transitions, but the same Markov chain or the same like causal structure, right? So it's interesting to show that this actually works. When a transformer model is trained, it sees a variety of data with different structure, right? So there's gotta be some kind of a routing to figure out, right? So when you do integer with XY type versus if you do it with other kind of causal structure, you figure out which one is which and how to use that from the existing pre-training data and match that to
Sounds like maybe like some nearest neighbor to find
the
the format that most matches.
Any thoughts on the routing behavior?
I think I've thought about this one. I feel like I've seen a paper on Archive.
Okay.
But I forgot. I need to look it up. I haven't really thought. Yeah.
So you mentioned the setting of Gar's paper, like linear regression and like layer one and functionality. So, but does this like analysis extend to their setting? Because I guess in their setting you need NLP and more layer always helps.
It only applies to their setting when everything was discrete states. Right? But in probably most of or all of their experiments, they use X is continuous, Y is continuous. In that case, this is the case you do need NLP. What you need to do is it's necessary to first learn the graph structure. And then once you know the graph structure, the MLP will approximate the F star function.
But even in this case, it seems like 2 layers should be sufficient, but
2 layers with an MLP is sufficient.
yeah, but I guess because run like some experiment, you like get like a huge benefits if you add like third or even go off the 8 layers.
For that setting?
Yeah.
Interesting. I'm not sure why.
Nice.
Yeah, I think in terms of representation, 2 layers is sufficient.
And do you believe like in the like another line of work they say that like this transformer like implementing some algorithm in the forward pass, like one is supposed GD or each layer has another reciprocal GD.
I believe it's solving the problem in distribution, but I don't think, I think the most convincing thing in that line I've seen is the GD stuff. Which is, I think they have, I think was it Ron Ge has an empirical paper. But at least when the X was isotropic, and it's like well-specified linear regression, I think the experiments were pretty convincing. It follows this GD++, which itself is, yeah, it's like I don't even know how to describe it. It's like, it's a method that will get quadratic convergence but it's sort of like the Newton-Scholz iteration to compute like an inverse or matrix square root or inverse. And then like it's implicitly doing this. I think it's something not easy to think of. Yeah. Yeah. And the guy found it by staring at the transformer, but yeah, so like there's some uses. Yeah.
Then let's thank Jason again.